Welcome to our exploration of haloalkanes and haloarenes, two important classes of organic compounds. In this video, we'll break down their structures, properties, and reactions, making complex chemistry concepts easier to grasp. Let's begin with haloalkanes. Haloalkanes, also known as alkyl halides, are compounds where one or more hydrogen atoms in an alkane are replaced by halogen atoms like chlorine, bromine, or iodine. These compounds are widely used in industry and laboratories due to their unique reactivity. Understanding haloalkanes sets the foundation for appreciating their chemical behavior and applications. Haloalkanes have a simple structure, an alkane backbone with one or more halogen atoms attached. The carbon-halogen bond is polar due to the difference in electronegativity between carbon and halogen atoms. This polarity influences the compound's physical and chemical properties, such as boiling point and solubility. For example, the presence of a chlorine atom in chloroethane makes it more reactive than ethane. The structure also determines how haloalkanes interact with other chemicals, which is crucial for understanding their reactions. Haloalkanes are classified based on the number of halogen atoms and the type of carbon to which the halogen is attached. They can be primary, secondary, or tertiary, depending on whether the halogen is bonded to a carbon atom attached to one, two, or three other carbons. Additionally, they can be mono, di, or polyhalogenated, depending on the number of halogen atoms present. This classification helps chemists predict the reactivity and properties of different haloalkanes. Haloalkanes exhibit distinct physical properties compared to their parent alkanes. The presence of halogen atoms increases the molecular weight and often raises the boiling point. Haloalkanes are generally insoluble in water but soluble in organic solvents. Their density also increases with the size and number of halogen atoms. These properties are important for their separation and identification in laboratory settings, as well as for their practical uses in industry. Chemical properties of haloalkanes are largely determined by the polar carbon-halogen bond. This bond makes them susceptible to nucleophilic substitution and elimination reactions. Nucleophiles, such as hydroxide ions, can attack the carbon atom, replacing the halogen. Alternatively, elimination reactions can occur, resulting in the formation of alkenes. The type of halogen and the structure of the haloalkane influence which reaction pathway is favored. Nucleophilic substitution is a key reaction for haloalkanes. In this process, a nucleophile replaces the halogen atom. There are two main types, SN1 and SN2. SN1 reactions occur in two steps and are favored by tertiary haloalkanes, while SN2 reactions happen in one concerted step and are typical for primary haloalkanes. The choice between SN1 and SN2 depends on the structure of the haloalkane and the strength of the nucleophile. Elimination reactions are another important pathway for haloalkanes. In these reactions, the haloalkane loses a halogen atom and a hydrogen atom, resulting in the formation of an alkene. The most common elimination reaction is the E2 mechanism, which occurs in a single step. The competition between substitution and elimination depends on factors like the strength of the base, the structure of the haloalkane, and reaction condition. Haloalkanes can be prepared through several methods. One common approach is the halogenation of alkanes, where alkanes react with halogens under specific conditions. Another method involves the reaction of alcohols with halogenating agents, such as thionyl chloride or phosphorus tribromide. Each preparation method offers different yields and selectivity, making them suitable for various applications in organic synthesis. Haloalkanes have a wide range of uses in industry and research. They serve as solvents, refrigerants, and intermediates in the synthesis of pharmaceuticals and agrochemicals. Some haloalkanes are used as anesthetics, while others are important in the production of polymers and plastics. Their reactivity and versatility make them valuable in many chemical processes. Now let's shift our focus to haloarenes. Haloarenes, also known as aryl halides, are aromatic compounds where one or more hydrogen atoms on the benzene ring are replaced by halogen atoms. These compounds exhibit unique properties due to the aromatic ring stability and the influence of the halogen. Haloarenes play a significant role in the synthesis of dyes, drugs, and pesticides. Structure of haloarenes is based on the benzene ring, with halogen atoms directly attached to the aromatic system. This arrangement affects the electron distribution in the ring, making haloarenes less reactive towards nucleophilic substitution compared to haloalkanes. The position of the halogen on the ring, ortho, meta, or para, also influences the compound's reactivity and physical properties. Haloarenes have distinct physical properties compared to haloalkanes. They are generally less volatile and have higher melting and boiling points due to the aromatic ring stability. Haloarenes are insoluble in water but dissolve well in organic solvents. These properties are important for their use in industrial processes and for their identification in the laboratory. Chemical properties of haloarenes are influenced by the aromatic ring and the attached halogen. Unlike haloalkanes, haloarenes are less reactive towards nucleophilic substitution due to resonance stabilization. However, they can undergo electrophilic substitution reactions, such as nitration and sulfonation, where the halogen directs the incoming group to specific positions on the ring. Nucleophilic substitution in haloarenes is much less common than in haloalkanes. The aromatic ring's resonance stabilization makes the carbon-halogen bond stronger and less susceptible to attack by nucleophiles. However, under certain conditions, such as the presence of electron-withdrawing groups or high temperatures, nucleophilic substitution can occur, leading to the formation of new aromatic compounds. Electrophilic substitution is the primary reaction for haloarenes. The halogen atom, while deactivating the ring towards further substitution, directs incoming electrophiles to the ortho and para positions. This directing effect is important in the synthesis of various aromatic compounds, including dyes and pharmaceuticals. Understanding this mechanism helps chemists design targeted reactions for specific products. Haloarenes can be prepared by direct halogenation of aromatic compounds, usually in the presence of a catalyst like iron Roman 3 chloride. Another method involves the Sammeyer reaction, where an aromatic amine is converted to a haloarene using copper salts and halogen acids. Each method offers different advantages depending on the desired product and reaction conditions. Haloarenes are widely used in the synthesis of dyes, pharmaceuticals, and pesticides. Their stability and reactivity make them valuable intermediates in organic synthesis. For example, chlorobenzene is used to produce phenol, while bromobenzene is a precursor for various organic compounds. The versatility of haloarenes ensures their continued importance in chemical industries. Let's compare haloalkanes and haloarenes. While both contain halogen atoms, their structures and reactivities differ significantly. Haloalkanes are more reactive towards nucleophilic substitution, while haloarenes favor electrophilic substitution. The aromatic ring in haloarenes provides extra stability, making their chemical behavior distinct from that of haloalkanes. This comparison highlights the diversity within organic chemistry. Both haloalkanes and haloarenes can have significant environmental impacts. Some haloalkanes, like chlorofluorocarbons (CFCs), contribute to ozone depletion. Haloarenes, especially those used in pesticides, can persist in the environment and affect ecosystems. Understanding their environmental effects is crucial for developing safer alternatives and responsible usage. Proper safety and handling are essential when working with haloalkanes and haloarenes. Many of these compounds are toxic, flammable, or volatile. Always use appropriate protective equipment, work in well-ventilated areas, and follow safety guidelines. Understanding the risks associated with these chemicals helps prevent accidents and ensures a safe laboratory environment. Testing for haloalkanes involves specific chemical reactions. The silver nitrate test is commonly used, where a haloalkane reacts with alcoholic silver nitrate to form a precipitate of silver halide. The color of the precipitate indicates the type of halogen present. This test is a simple and effective way to identify haloalkanes in the laboratory. Testing for haloarenes is more challenging due to their lower reactivity. One method involves heating the compound with sodium in the presence of alcohol, known as the sodium fusion test. The resulting solution is then tested for halide ions. This process helps confirm the presence of halogens in aromatic compounds. Some haloalkanes and haloarenes have biological effects, both beneficial and harmful. Certain haloalkanes are used as anesthetics in medicine, while others can be toxic or carcinogenic. Haloarenes, especially those used in pesticides, can affect human health and wildlife. It's important to understand these effects for safe usage and environmental protection. Let's look at some common haloalkanes. Chloroform, once used as an anesthetic, is a well-known example. Carbon tetrachloride is used as a solvent and cleaning agent, though its use is now restricted due to toxicity. Methyl chloride and ethyl bromide are also widely used in industry. These examples illustrate the diversity and utility of haloalkanes. Common haloarenes include chlorobenzene, used in the production of phenol, and bromobenzene, a precursor for organic synthesis. Iodobenzene is another example, often used in coupling reactions. These compounds are essential building blocks in the chemical industry, highlighting the practical importance of haloarenes. Reactivity of haloalkanes depends on the type of halogen and the structure of the molecule. Generally, iodides are more reactive than bromides, which are more reactive than chlorides. The nature of the carbon-halogen bond and the surrounding groups also influence reactivity. Understanding these trends helps predict reaction outcomes and design efficient syntheses. Haloarenes are generally less reactive than haloalkanes due to the resonance stabilization of the aromatic ring. However, the presence of electron-withdrawing groups can increase their reactivity towards nucleophilic substitution. The position of the halogen and other substituents on the ring also play a role in determining reactivity. SN1 reaction mechanism involves two steps. First, the halogen leaves, forming a carbocation intermediate. Then the nucleophile attacks the carbocation, resulting in substitution. This mechanism is favored by tertiary haloalkanes, where the carbocation is stabilized by surrounding groups. The SN1 pathway often leads to racemization due to the planar nature of the intermediate. SN2 reaction mechanism occurs in a single, concerted step. The nucleophile attacks the carbon atom from the opposite side of the leaving group, resulting in inversion of configuration. This mechanism is typical for primary haloalkanes, where steric hindrance is minimal. The SN2 pathway is highly sensitive to the structure of the substrate and the strength of the nucleophile. E2 elimination mechanism involves the simultaneous removal of a hydrogen atom and a halogen atom from adjacent carbons. This one-step process leads to the formation of an alkene. The E2 mechanism is favored by strong bases and occurs more readily with secondary and tertiary haloalkanes. Understanding this mechanism is key for designing elimination reactions. The E1 elimination mechanism is a two-step process. First, the halogen leaves, forming a carbocation intermediate. Then a base removes a hydrogen atom, resulting in the formation of an alkene. The E1 mechanism is similar to SN1 and is favored by tertiary haloalkanes. This pathway often competes with substitution reactions under similar conditions. Choice of solvent can significantly affect the outcome of reactions involving haloalkanes and haloarenes. Polar product solvents favor SN1 and E1 mechanisms, while polar aprotic solvents favor SN2 reactions. Understanding solvent effects allows chemists to control reaction pathways and optimize yields in organic synthesis. Stereochemistry plays a crucial role in the reactions of haloalkanes and haloarenes. SN2 reactions result in inversion of configuration, while SN1 reactions can lead to racemization. The spatial arrangement of atoms affects the properties and biological activity of the resulting compounds, making stereochemistry an important consideration in synthesis. Polyhalogenated compounds contain more than one halogen atom. Examples include dichloromethane and trichloroethylene. These compounds often have unique properties and uses, such as solvents or intermediates in chemical synthesis. However, they can also pose environmental and health risks, highlighting the need for careful handling and regulation. Aromaticity is a key feature of haloarenes. The delocalized electrons in the benzene ring provide extra stability, affecting how these compounds react. This stability makes haloarenes less reactive towards nucleophilic substitution but more selective in electrophilic substitution. Aromaticity is central to understanding the chemistry of haloarenes. Industrial synthesis of haloalkanes and haloarenes involves large-scale reactions under controlled conditions. Processes like chlorination of methane or bromination of benzene are optimized for yield and safety. These industrial methods supply the raw materials needed for pharmaceuticals, plastics, and other products, demonstrating the practical importance of these compounds. In the laboratory, haloalkanes and haloarenes are synthesized using smaller-scale methods. Reactions are carefully controlled to achieve high purity and selectivity. Techniques such as distillation and recrystallization are used to isolate and purify the products. Laboratory synthesis is essential for research and the development of new compounds. Green chemistry aims to reduce the environmental impact of chemical processes. For haloalkanes and haloarenes, this means developing safer synthesis methods, using less hazardous reagents, and minimizing waste. Advances in green chemistry help make the production and use of these compounds more sustainable and environmentally friendly. Study of haloalkanes and haloarenes has a rich history. Early chemists discovered these compounds while investigating the properties of natural and synthetic substances. Over time, their understanding of structure and reactivity led to major advances in organic chemistry. Today, these compounds remain central to research and industry. Research on haloalkanes and haloarenes continues to evolve. Scientists are developing new reactions, safer compounds, and more efficient synthesis methods. The future holds promise for greener processes, novel applications, and a deeper understanding of these fascinating molecules. Staying updated with current research ensures continued progress in organic chemistry. Summarize the key points covered in this video. We explored the structures, properties, and reactions of haloalkanes and haloarenes. We discussed their preparation, uses, and environmental impact. Understanding these concepts is essential for anyone studying organic chemistry or working in related fields. Mastery of haloalkanes and haloarenes opens the door to advanced topics and practical application. To reinforce your understanding, try solving some practice problems related to haloalkanes and haloarenes. Identify the type of reaction, predict the products, and explain the mechanisms involved. Practice is key to mastering organic chemistry concepts and applying them effectively in exams and real-world scenarios. For those interested in learning more, numerous textbooks and online resources cover haloalkanes and haloarenes in detail. Exploring these materials can deepen your understanding and provide additional examples and exercises. Continuous learning is essential for success in organic chemistry and related disciplines. Haloalkanes and haloarenes are present in many products we use daily, from refrigerants and solvents to pharmaceuticals and plastics. Their unique properties make them essential in modern life. Understanding their chemistry helps us appreciate the science behind everyday materials and encourages responsible use. Thank you for joining this comprehensive journey through haloalkanes and haloarenes. We've covered their structures, reactions, uses, and significance in organic chemistry. With this knowledge, you're better equipped to tackle advanced topics and appreciate the role of these compounds in science and industry. Keep exploring and stay curious about the fascinating world of organic chemistry.